Alright, in this video we're going to talk about Unit 3, Objective 3, definite integrals. So we saw in the last section that the inverse of a derivative is called the antiderivative. And we're going to end up using those antiderivatives to help us find area under the curve. So we're going to use antiderivatives to find the exact area under the curve on a given interval using the fundamental theorem of calculus. So we've seen a couple times, or a couple different ways where we found area under the curve. We estimated using Riemann sums and trapezoids. We found exact area if we had piecewise functions made up of linear functions. That way we can use rectangles and triangles to come up with exact area. But now we're actually going to be able to find the area under a curve and using our fundamental theorem of calculus. So what the fundamental theorem of calculus says is that f is continuous at every point on some closed interval a to b, and capital F prime of x equals f of x. So what that is saying is that capital F of x is the antiderivative of f of x. So the stuff that we did in that last section where we found antiderivatives, we were finding this capital F of x. So there is a difference between capital and lowercase f. So f of x, capital F of x, is the antiderivative of lowercase f of x. Then our integral from a to b of f of x dx is going to be equal to capital F of b minus capital F of a. So we're going to find the antiderivative. We're going to plug in b, or we're going to plug in a, and we're going to subtract, and that's going to give us the exact area under the curve. So since this only works on the interval a to b, we need to make sure that our limits of integration are in the same order. So what that means is if a is less than b, right, so our interval a to b, a's got to be the smaller number, then the integral from b to a, right, so we're switching the order, is going to be equal to the opposite of the integral from a to b of f of x dx. So we have to pay attention to the order of our limits of integration. If they don't go from the lower number to the bigger number, smaller to the bigger number, we have to switch the order and then put a negative outside. Also, we need to remember that the only rules that we have for antiderivatives are the power rules. So the power rule and our trig rules. So we still, at this point, don't have a quotient rule, we don't have a product rule, we don't have a chain rule. It's just the power rule and our trig rules. So let's look at an example or a couple of examples of how we use our fundamental theorem of calculus. So this first problem wants us to find the integral from -2 to -1 of 2 over x squared. So the first thing we need to think about is that's a quotient, and we don't have a quotient rule. So we need to rewrite this using our power rule. So we can rewrite that as 2x to the -2nd power dx, and that's just with respect to x is how we're going to say that. So from -2 to -1 of 2x to the -1st dx. So what we can think about is we know what our antiderivative is from the previous section. We want to increase our exponent by 1, so that's going to make this x to the -1st. And then we want to divide by that new exponent. So our antiderivative can be simplified to being -2 over x. Or if you want to keep it as -2x to the -1st, that's fine. The reason I'd like to write it this way is because we want to evaluate that from -2 to -1. So this little bar just means evaluate from -2 to -1, which means take f of b minus f of a, like our fundamental theorem says, so f of b minus f of a, and then we just subtract. So put -1 in there, we're going to get -2 over -1 minus -2 over -2. This is going to turn out to be 2 minus 1, positive 1, so our total answer here is going to be 1. So all we're doing is we're finding our antiderivative. We're going to evaluate it from a to b, which means we're going to do f of b minus f of a like our fundamental theorem of calculus tells us to do. So our second question is going to be the integral from 0 to pi of 1 plus cosine x dx. So we want to anti-differentiate. We can do it since there's a plus sign. We can kind of break it up and think about it as two different integrals, the integral of 1 and the integral of cosine of x. but we're going to end up putting them back together anyway. So we can just say that our antiderivative is going to be, if we think about 1 as 1x to the 0 power, because x to the 0 is 1 times 1, increase this power by 1, so it's going to be x to the first power times that 1 divided by 1, so it's just going to be x. And if you think about antiderivatives, it's really saying what function has a derivative of 1. So x has a derivative of 1. Then we have to think about cosine. The antiderivative of cosine is going to be sine of x. A really easy thing to make a mistake on there is to say negative sine, but remember our little circle, the little clock thing. Cosine's here. If we're taking an antiderivative, we go counterclockwise, and that's going to give us positive sine. And then we're going to want to evaluate that from 0 to pi. So our integral is going to be equal to pi plus sine of pi. So f of b minus f of a. So that's going to be 0 plus sine of 0. Oh, not theta, but 0. So sine of pi is 0. Sine of 0 is 0, so our answer here is just going to be pi. Now, one thing that I'd like to mention is the plus c that we have to take when we find our antiderivative. Really, when we think about this problem, our antiderivative, our capital F of x, should be x plus sine of x plus c, and we should evaluate that from 0 to pi. But what's going to happen when we do that is we're going to get pi plus sine of pi plus c minus 0 plus sine of 0 plus c. And this plus c minus plus c are going to cancel out every single time on every single problem. So if we're finding a definite integral, we don't really need to worry about our plus c because they're going to end up canceling each other out. All right, so we have one more question, and this is going to be one that we have to use a calculator on. So it says, let f prime be f of x be the natural log of x minus 3 to the second power over x. If capital F of 1 equals 2, then capital F of 2 equals what? So this is a type of question that AP likes to do. We got to remember, they're telling us here that f prime equals f. So they're telling us there that capital F of x is the antiderivative. So what we want to think about here is they're giving us two capital F values. Well, they're giving us one and they're asking for another. The only thing that we know that relates to antiderivatives is f of b minus f of a. And that's actually going to be equal to the integral from a to b of f of x dx, according to our fundamental theorem of calculus. So when we are given two antiderivatives like we are in this problem, we want to think about our second fundamental theorem of calculus. Then we're just going to plug things in and see what happens. So a has got to be the smaller number, b has got to be the greater number. So a is 1, b is 2. So we're looking at this and we're saying, all right, f of 2 minus f of 1 equals the integral from 1 to 2 of, we know f of x is going to be this natural log of x minus 3 squared over x dx. We know f of 1 is 2. They tell us that up here. And so if we add f of 1 to each side, because we're trying to figure out what f of 2 is, we know that capital F of 2 is going to be equal to the integral from 1 to 2 of the natural log of x minus 3 squared over x dx plus 2. So we don't know how to do this because there's a bunch of things going on here. 1, it's a quotient. 2, there's a natural log. 3, there's chain rule. There's all kinds of stuff in this that we don't know how to do. And it turns out that we're never going to be able to do this one by hand. So we have to actually plug this into our calculator to figure out what f of 2 actually is. So how we're going to use our calculator is we want to hit the alpha button and then the window button. And number 4, FNINT, is going to give us an integral. And now it's just plugging in everything that we need to know. So we're going from 1 to 2 if we hit alpha y equals, that first option there lets us put in a fraction, so it's really nice and easy. We don't have to worry about parentheses too much. In the top of our fraction, we had the natural log of x. Make sure you close these parentheses because the minus 3 is not part of your natural log. Close those parentheses so we can square over x, and then dx, and go ahead and hit enter. Now that is the value of the integral, but that's not the value of f of 1 because we had to, f of 2, because we had to add 2. So our answer is actually going to be 6.908 for f of 2. So f of 2 equals 6.908. So that's going to do it for this video. We will see you in the next one.